So this part of the tutorial is designed as a introductory course on how to quickly get started on DAOS, and just a brief overview of DAOS. But we also have a detailed in-depth full day session next week where we'll cover more details about DAOS. So with that, we'll get started. So why do we? Yeah. So why do we need DAOS? So DAOS is a major file system in Aurora with 1024 DAOS server nodes with a total capacity of 230 petabytes, and it can deliver up to 25 terabytes per second. Uh, so DAOS is Distributed Asynchronous Object Store. Uh, it's an open source software-defined object store. It's designed for massively distributed non-volatile memory and NVMe SSDs. So DAOS presents a unified storage model with native key value array um, uh, and different storage interfaces. You can use like POSIX, MPIO, HDF5, and if you want a detailed, like even a direct DFS interface, which will give you even a faster performance. So the storage and retrieval of all the objects are distributed and in parallel and in a synchronous manner. And it also has other features like data protection, self-healing, redundancy versioning, and more fine-grained controls. So today, Aurora has the largest DAOS system, and we also rank number one in the IO 500. You can also see many other top 10 IO 500 systems use DAOS. So on Aurora, we have two major file systems. One is DAOS, the other option is Lustre. So the Lustre file system on Aurora is called FLAR, and the total capacity is around 91 petabytes. But the peak performance that we can get out of FLAR is roughly half a terabyte per second. Home is also a Lustre file system, but it is for lightweight purposes, and if you're launching jobs, you should use the FLAR space. Whereas if you compare with DAOS has 230 petabytes, and it can deliver up to 25 to 30 terabytes per second. Currently, we have two different clusters of DAOS, which is called DAOS User and DAOS Perf. Each has 128 DAOS servers. So today, applications are reaching around 5 terabytes per second. I also have an example which I will share class. So, and if you look at the slingshot network architecture, you can see that so all the blue ones are the compute nodes, and the red ones are the DAOS nodes. And our FLAR is actually connected to our gateway nodes. So there is some kind of bottleneck. It's not directly connected to the compute network fabric, but whereas DAOS, you can see that each cabinet has at least one direct link to the DAOS groups. So that's where that's one architectural way of squeezing the best out of the compute network fabric. Moving on to the DAOS ecosystem and the design fundamentals. So DAOS is really efficient if you have unstructured data, and especially if you are accessing small data. It provides high bandwidth, low latency, and high IOPS. So there is this concept of versioning. So there is no read, modify, write. So if you want to change the data, only the latest version gets stored. And so by this way, there is no locking, no file locks or no delays. And there's no client tracking in case of a crash or recovery. It is completely decentralized, and all the metadata is decentralized, and there's no one single global object state. So DAOS has both the persistent memory as well as the NVMe SSDs. So in each DAOS node, we have one persistent memory and one SSD. And together, this we call it as an engine. Uh, I'll go over the DAOS hardware architecture in the next slide. But so what happens is when you're writing a data, if all the small data which is less than 4K goes to the persistent memory, and all the and later it gets written down to the NVMe SSDs. So by this way, we get high IOPS and we get the best out of persistent memory here. For other systems which don't have Intel opt-in DC persistent memory, we can always there's also another mode where they use the DRAM for the persistent memory. So this object store now unlocks all previously expensive I/O patterns and supports different file creation, querying, analysis, and usage patterns. And it leverages the metadata and build the structure on the fly. So, for example, if you have weather data with a lot of parameters like pressures, humidity, and so on, in one dimension, we have many different years on the other dimension. Previously, with Lustre, accessing certain slices are expensive because you have to load the entry data and there's file misses and cache misses. But with object stores, you can use the metadata to form the structure and then query different objects on the fly. And similarly, another example with radio astronomy. The data can be collected and stored by different antennas across different time, and the reconstruction of images is done on the time. You can do all sorts of evaluation with transient lightweight features. So here I'm showing one single Aurora compute node and one single DAOS storage node. So on a compute node, you can see that there are 8 NICs. So each NIC board has 2 NICs, so totally 8 NICs here. And on a single DAOS node, you have 2 NICs. So it is important to use all the NIC bindings efficiently. I'll cover that in the next slide. But you can see that with 8 NICs, each NIC delivering 25 gigabytes per second can deliver up to 200 gigabytes per second. And we see that in just one node, and you just need around 20 to 32 ranks per node to reach the peak performance. On a DAOS node, as I said before, we have both persistent memory as well as SSDs. So we have 16 Intel opt-in persistent memory and 16 SSDs. So each SSD is around 15 terabytes and each persistent memory is around half a terabyte. So this is just a single DAOS node. And if you combine one persistent memory and one SSD, we call it as a one DAOS. So we have 2 DAOS engines, and each of this device is called a target. So totally 32 targets and 2 engines per DAOS server. So this is again connecting to the previous slide, just to use efficiently all the 8 NICs on Aurora, and this is a recommended CPU binding. So if you are using 12 ranks per node, we use 12 GPUs. So this is just a recommended core to NIC binding where you efficiently use all the 8 NICs. So the first step to use DAOS is to request for a pool allocation. So each project gets a DAOS pool. It's a dedicated storage space. So you just have to email the support with the following details to request a pool. So to get started with DAOS, there are just 5 steps. The first step is just module load DAOS. In the second step, you just make sure the pool that you requested and is active and you have access to it. So pool is, as I said before, it is one dedicated storage space uh, with so you can run this DAOS pool query data science and you can see how much of SSD space you have and how much of memory space you have. This is the quick way to verify and get started. This is the second step. And the third step is once you have access to your pool, you have to create a container. So you can think of container as a directory in a very simple word. Uh, Under a pool, you can create as many directories as you want, but preferably to have fewer containers. And you can just treat them like the directory file structure. So to create a container, you just give DAOS container create and specify the type as POSIX container, give pool name, the container name that you want. And you can pass this properties to enable checksum and to have redundancy factor of 2. So this redundancy factor is you have 2 copies if you want reliability and if you want to rebuild your data in terms of data recovery. And you also have other tools here to query your container, get the properties and list and check, destroy. But this is all that's needed to create a container. So once you create a container, the fourth step is to mount it. So you can mount it either in the login node or in the compute node, and you can use it uses fuse. So start diffused is used to mount on a login node. You just give the path where you want to mount and provide the pool name and the container name. And so you just have to add this $user in case 2 other users are mounting in the same space. On a compute node, we have the script launch diffuse. It just uses Flash on the background to do this on all the compute nodes. So this is the first step. So once you mounted, you can just CD to the directory and do an LS and redirect all your inputs and outputs and checkpoint to that location and start using it as like a normal POSIX. So the last step is an interception library. So we have this libpl for DFS, so which when you're using this POSIX container, both the metadata and data is intercepted, and it provides more higher performance close to the libdfs the DFS node. So this is the last step to get started. You just have to pass this LD preload of libpl for DFS. And previously we had this libiol where only data is intercepted, but it's no longer recommended. So that's all you need to get started with. So there are different types of interfaces with DAOS. We have the POSIX interface, which we just went through. Once you mounted your container, you can just CD to the space and LS and start using it. So you can also use a space to store all your MPIO or HDF file directly there and use that interface from POSIX. So there is also this DFS interface, which actually this POSIX interface itself gives very good performance, very close to the DFS. But yeah, in case if you want to develop your own low-level IO code, you can use the DFS interface. So, and you just start with slash. Once you create the DFS container, you just provide the slash and provide the file name and interact with it directly. So there is also a PyDAOS interface, which I have tested and it is working. So you can also uses PyDAOS for torch or data loaders or checkpoints. Uh, these are the different ways to interact with the DAOs. So just a quick reminder, on your job script, you have to pass -l DAOS equal to DAOS user. That's the cluster that we have now. And add DAOS underscore user new file system. This is the only change uh, with and without using DAOS. And this is how a simple job script would look like. So uh, here I added the -l file system DAOS user and -l DAOS equal to DAOS user here. Added the module load DAOS, DAOS container create to create a container, and then I mount it on all the nodes, and you can cd to that directory and use this to store all your files. So you can see that I copied my input data from Luster space to the DAOS space, and I'm using it directly on my LPA exit and the LDP load of libp for device. You don't have to give this clean diffuse. It is added in the epilogue. So by default, when the job ends, all the nodes and the clean diffuse. This is the simple jobs that get started with DAOS. And this is a recent result from Hack. Uh, um, so you can see that with 5 nodes and 12 ranks per node, with Luster, in the Luster space, we are able to get around 600 gigabytes per second bandwidth. And the only change is instead of writing all the data to a Luster space, we just changed it to the tool name, container name, DAOS space. And we got around 5.2 terabytes per second. And this is just with 10% of the DAOS nodes, 128 out of 1024 DAOS with POSIX content. So this is one of the results. And I think I'm almost near the end of my presentation. So we have the DAOS overview documentation. We recommend to, it's constantly being updated with new recommendations. You can start from here. And we also have a detailed tutorial next week, May 13th, where we'll cover more in-depth details. And I would like to thank support from ALCF Ops, HP based team. That's it. Thank you.